Welcome to another lecture. In this lecture, we are going to talk about maximum power transfer. That is how we can transfer the maximum amount of power from a circuit to one of its specific circuit component. So what do I mean by that? I think a hypothetical example might be very good here. So let's say you have your laptop, but the charging indicator, the light that turns on when you connect the charger to your laptop, doesn't work in your laptop. Okay, so this is broken and you want to change that light bulb. So you go to your local electric shop and they give you a choice of different light bulbs. Okay, so there are obviously different types of light bulbs. By the way, I think a short note might be very good here. So I'm only talking about simple old light bulbs. Okay, so I'm not talking about LEDs or something like that because we have not yet studied diodes and etc. Okay, so I'm just going to talk about simple old incandescent light bulbs because these are just fancy resistors. Okay, so resistors that can convert electrical energy into light and heat energy. Okay, so these are just simply resistors. That's why we are going to talk about simple light bulbs, but still there might be various types of light bulbs, because this might have a 1 ohm light bulb, this might be 10 ohm or etc. So maybe you have a 1 ohm light bulb, then you have a 10 ohm light bulb, then you have a 100 ohm light bulb, and you might even have 10 kilo ohm light bulbs. Okay, so which one of these light bulbs do you choose? So just by luck, you want to choose one. You just try out every one of them. Okay, so maybe you want the brightest light, so maybe you use the 10 kilo ohm one. When you use the 10 kilo ohm one, what happens is that the light turns on, but it's very, very dim. Okay, so you don't like that, you want the brightest light. So you change that 10 kilo ohm light bulb and use the 1 ohm light bulb. So maybe you are thinking, okay, the low resistance might be helpful, so use the 1 ohm light bulb. But turns out this is also very dim. It doesn't glow very brightly. Okay, and you try out one by one, and turns out that the 200 ohm light bulb is the best one. So when you use the 200 ohm light bulb, that light glows the brightest. So what's happening here? Okay, that's what we are going to discuss. So first of all, we need to understand that this light bulb is actually connected to the laptop circuitry. So definitely this is a very complicated system. This light bulb is connected to a very complicated system, and even the laptop itself is connected to the charger, and that's connected to the national grid. So in a sense, this a small light bulb is actually connected to the whole national grid system. So we need a way to simplify everything. And we have actually learned that in Thevenins Theorem, right? So in Thevenins Theorem, what we do is simplify any complex linear circuit. So if you have a circuit, let's say for simplicity's sake, if you have any circuit, you can convert that into just one voltage source and a resistance, right? So maybe the whole complicated laptop guts, I'm calling it laptop guts, plus everything else, okay, is just this circuit. So we also call it this V Thevenin, and we call it Thevenin's resistance R Thevenin. And you are just focusing on your light bulb. So what you are doing is changing out these light bulbs. You have first you try the 10 kilo ohm one, then you try out the 1 ohm one, then after a lot of this, you happen to use the 200 ohm light bulb, and maybe it's the brightest. Okay, so what's going on? That's what we are going to focus on here. Okay, so I think a value might be very good here. Okay, So let's say the Thevenin's voltage here was 10 volt. Okay, and the Thevenin's resistance was, let's say, 200 ohm. Okay, so 200 ohm. This is the Thevenin's resistance. So this is the laptop guard's equivalent resistance. Okay, this is not the light bulb. And first of all, you are using the 10 kilo ohm one. Okay, so you are using the 10 kilo ohm light bulb. What will happen here? So as we can already see that this resistance is much larger than the 200 ohm light bulb, and this will actually cause the voltage to be higher here than these resistors. Okay, so how can I actually claim that this voltage is actually larger than this one? Well, you can see that by using the voltage divider rule. Okay, so let's say the voltage here is VL. The voltage across our light bulb is VL. And we can calculate the value of VL using the voltage divider rule. So we have 10 kilo ohm on top, and at the bottom we have 200 ohm plus 10 kilo ohm, the whole series resistance, and everything times 10 volt, because we have 10 volt supply on both of them. Okay, so if you do the calculations, you will get 9.8 volt. Okay, so that means out of this whole 10 volt, we have 9.8 volt across our light bulb, and only 0.2 volt across this 200 ohm. And we are interested in brightening up our light bulb. So if we have the 98% of the voltage, doesn't that mean our light bulb will glow the brightest? Well, actually no. So here's the thing. Even though we have the highest voltage here, and in fact if you raise the resistance here, the voltage here would increasingly grow up to 10 volt. Okay, so there's no doubt the voltage is higher here, but the problem is the current. So even if you have a high amount of voltage, but there's only a little current, so let's say you have, okay, for the extreme case, let's say if there was only no current at all, so 0 ampere current, definitely the power would have been V times I, the voltage 9.8 times the current 0 would still give you 0 watts of power, right? So definitely just the voltage doesn't play the whole role here. You have to also consider the current. Okay, and in fact let's not consider here 0 ampere. We can actually calculate this current, and if we do calculate the current, we should get I equals to 9.8 volt divided by 10 kilo ohm, because of Ohm's law, right? Voltage divided by resistance. And if we do the calculation, we will get 0.98 milliampere. And so if we use the actual values, we will have 9.8 volt times 0.98 milliampere, and the whole thing would turn out to be around now 9.6 milliwatt. Okay, so this is our actual power. So here's the thing. So even though your voltage is high, your current might be so low that the power is lower. And in fact, the same thing actually works in reverse too. So let's talk about the 1 ohm case right now. Okay, so let's draw the circuit again. We have the same laptop guts, so 10 volt and 200 ohm, but we have a new resistor here. So we are trying out the 1 ohm case here. Okay, so now what happens? So this time you may think, okay, so if the resistance is very low, the current might be very high, right? So yeah, of course the current here is higher, so we can actually in fact calculate the current. So the current would be the same throughout the whole loop because they are in series. And if you calculate the current, you would get I equals to you can use the total voltage 10 volt divided by the total resistance, right? So 201 ohm. And if you do the calculation, you would get 0.0497 ampere, or I think it would be better to if we write in milliamperes. So we will have 49.7 milliamperes. Okay, so definitely the current is higher than before. This was less than 1 milliampere before, and now it's like around 50 milliamperes. So it's like 50 times higher than before. Okay, so the current is higher, but now the problem will be the voltage. So if we use if we calculate the voltage like we did using the voltage divider rule, we would get 1 ohm divided by 200 ohm plus 1 ohm times 10 volt, which is equals to 0.0497 millivolt, volts. So which is basically in the millivolt zone, right? And if we calculate the power V times I, we would get 49.7 milliamperes times 0.0497 volt, and if we do the calculation here, we will get 2.47 milliwatt. Okay, so this time our voltage is lower, just like the previous time our current was lower. So there is definitely a balancing act between the voltage and current so that the power is maximum. Okay, so what happens, let me draw a picture. I am drawing some axes here. So this is our x-axis, which will contain resistance, and on the y-axis we will have voltage. So what we have seen in these two examples, so here we had 10 kilo ohm voltage, and when we had 10 kilo ohm voltage, the voltage 10 kilo ohm resistance, the voltage was 9.8 volt. So we had a very high voltage. But when we had 1 ohm resistance, the voltage was very low, like 0.049 volt. Okay, so the voltage was very low. That means if we increase the resistance, the voltage is higher, and this is actually backed up by the voltage divider rule. So in the voltage divider rule we have V, so VL, the voltage across the light bulb is actually RL divided by the 200 ohm plus RL times 10 volt, right? So I'm omitting the units, but you get the idea. The whole thing is voltage, in voltage. And if you actually plot the curve, you will see that this is actually a increasing graph. Okay, so the graph looks something like this. Okay, so if we increase the resistance, the voltage will actually rise. So the more resistance you have, the voltage will the higher the voltage you will get. Okay, so that's a good thing. If you increase the resistance, you will have higher voltage. But the problem is the current, right? So the current has a decreasing relationship with the resistance. So if we draw another graph here, so this is our resistance, and here we will draw current, right? And we know how we calculated the current, that our current was actually, we can use the whole 10 volt divided by the total current, so 200 plus RL, right? Whatever resistance we used. And if we actually plot the current, this will look something like this. So when the resistance is 0, you will get something a high value, and from then it will start to drop. Okay, so that's the balancing act. Since the power actually depends both voltage and on current, so you can't actually increase the resistance forever and get the higher value of voltage, higher value of power. So what I am trying to say is we have power's equation is voltage times currents. If you increase the resistance, the voltage rises, but the current drops. And if you lower the resistance, the current will rise, but the voltage will drop, as we can see from the graph. So exactly when will the power be maximum, right? We want the maximum amount of power, and that will be in somewhere in the middle. Okay, so if we draw the power graph, so that will actually just, if you multiply these two graph, you will get the graph here of power. So if we draw the power here, this will look something like this. Okay, so there will at some point this will have a maximum value. Okay, this will have a maximum value. And how can we calculate the maximum value for which resistance? So let's call it R max for let's say we are calling it R max. Okay, so what's this value of R max? Okay, that we get the most power. So this is our P max. If you do the calculations, I can go into the calculations in a later time, but well, maybe in live classes we'll go through the calculations. If we do that, you will see that actually this is exactly 200 ohm. Okay, so where did this 200 ohm come from? So at exactly 200 ohm, you will have the maximum amount of power. So in general, this is just one example we used with 200 ohm, but this was actually our Thevenin, right? So Thevenin's resistance. So in general, when your load resistance is actually equal to our Thevenin's resistance, you get the maximum amount of power. Okay, so that means your laptop guts have 10 volt times and there we have 10 volts, and here we have 200 ohm. This is inside your laptop. Okay, and if you choose a light bulb that has exactly 200 ohm resistance, you will have the brightest light. Okay, this will be the brightest light. So this is something we call resistance matching. So if you use the exact same resistance as here, you will have exactly the most brightest or the most power transfer. Okay, so that's why we call it maximum power transfer. So if you use matching resistance, you will have maximum power transfer. That's the whole thing. Okay, nothing actually really crazy here. So that's the whole idea. Hopefully this example has explained the whole thing, and we can go into the mathematics, but the main scenario here is that if you use the exact resistance as the Thevenin's resistance, you will have the maximum power. Okay, so for completeness, let's do another example. So maybe you have a circuit where you have 12 volt, and then you have here, let's say 500 ohm, and I can ask you two questions. For what resistance will you have the maximum power? So maximum power. So I want the value of the resistance. And second, another question I can ask you, what is the maximum power? So what's the value of P max? I can also ask that. Okay, so how can we answer that? Well, from the theory we just learned here, okay, I haven't shown, even though I haven't shown the proof, what we have learned is that if we use 500 ohm resistance here, we will have the maximum power. So answer to number one question is RL equals to 500 ohm. Okay, so previously I have used RL, so I kind of and VL, so I kind of cheated. I said this L stands for light, but actually this L stands for load. So like in load shedding, right? So the load means what uses something that uses power. Okay, so that's what we load mean. So this is our, I mean, here we are talking about like the point of our interest. That's the load. Okay, and this is our R Thevenin, and this is our V Thevenin. Okay, so the theorem says when your RL equals to R Thevenin, if you have a choice of loads, then you will have the maximum power. And since our R Thevenin here is 500 ohm, we will have the maximum power transfer at 500 ohm. And then in the second question, I am asking, okay, what is that maximum power? I understand that if you use the same resistance, you will have the maximum power. But what is the value of the maximum power? Well, that's actually very easy, because as you can see that the maximum power is when we have 500 ohm resistance, right? So that means the power right now, the power this resistance consuming right now is the maximum power. Okay, so let's calculate that. How can we calculate that? So we can do just I squared R, right? So here are L, obviously. So we have to calculate the current first. So how can we calculate the current? We can use the Ohm's law, the 12 volt, the whole voltage across the two resistors, divided by the total resistance. So 500 ohm plus 500 ohm. So this is equals to 12 milliampere. In SI unit, that is 12 to the power 12 times 10 to the power minus 3 ampere, right? The reason I did it because I want to go here, and if we do the calculation, so here we have the current 12 into 10 to the power minus 3 whole squared times resistance 500 ohm. And since we have used the SI units everywhere, so this will also have SI unit voltage. And if we do the calculation, so we have 12 squared, right? So let me do the calculation for a second. We will have 72 milliwatts. Sorry, I meant here watts. And if we do the calculation, we will have 72 milliwatts, or 0.072, whatever you want to write. So either way, this is our maximum power. And the way we can transfer the power is by using the 500 ohm resistance. So if you use something else here, so maybe 400 ohm resistor, you will see that the power is not actually as much as 72 milliwatt. It will be something less than 72 milliwatt. So and even if you use the 600 ohm resistor, you will see that's still less than 72 milliwatt. Okay, so only if you use the exactly 500 milliwatt, you will have the maximum power. That's the whole maximum power transfer thing. So thank you.